All right, folks, so now we're going to look at proving conjectures using deductive reasoning. We're going to talk about understanding deductive reasoning, general proofs about number, common general number representations, number tricks, and two-column proofs. Lots of things there. Okay, let's get going. So deduction is drawing a conclusion that is unquestionable. Unlike induction or inductive reasoning, where we get sort of a general idea, but we're not really sure if it's true, deduction is always true. So we start with general assumptions that are known to be valid. Let's look at this example. All natural numbers are whole numbers. That's true. All whole numbers are integers. That's a fact. 7 is a natural number. A fact. So these are what we call the premises, or the evidence that we're going to base this on. So natural belongs to the group of whole, which belongs to the group of integers. So if 7 is a natural number, then obviously it must also be a whole number and an integer. So most generally, we could say 7 is an integer. Okay, so we've established that 7 is an integer. That's a logical conclusion, and it can't be denied if we know that all natural numbers are wholes and all wholes are integers, then therefore 7 has to be an integer. You can't deny that, okay? So it's a mathematical argument establishing that the conjecture is true in all cases and that there are no counterexamples. That's not a very strong conjecture. Let's try some trickier ones. Number tricks are fun. Pick any number, double it, then add 3. Now subtract 1 and divide by 2 and subtract 1 again, and you always arrive at your original number. What? Okay, let's see if we can follow that with an inductive justification as well as a deductive proof. So pick any number, 4. Okay. Double it, we get 8. Add 3, we get 11. Now subtract 1, we get 10. Divide that by 2, we should have 5. And then subtract 1 again, we're going to have 4. And we should arrive at our original number. Hey, what do you know? It worked. Nice trick. Okay, so that's fine. It works for 4. But this number trick is supposed to work for all numbers. We have to prove that it'll work for any number. So how do we do that? Well, we can't check every number in the world. But what we do is we assign a variable like x, and we're going to prove it generally. Okay? So we're going to prove this generally. So if we have x, the first thing we have to do is double it. So we're going to have 2x. And the next thing we have to do is add 3. So 2x plus 3. And then it says now subtract 1. So 2x plus 3 minus 1 is going to be 2x plus 2. Okay? And then it says divide by 2. So if I take 2x plus 2 and I divide by 2, I'm going to get x plus 1. Okay? And then it says subtract 1 again. So x plus 1 subtract 1 just gives me x. And we arrived at our original number. And it worked for x, which was a general thing. It wasn't any specific number. So that should work for any number. X was just like a placeholder that went through here. No matter what number we put in there, we'd still get the same thing out. So that's the idea. We've proven it. And I like to write this for a proof. QED. Quod erat demonstrandum. A little Latin phrase that says, we proved it. Ha-ha. Okay. So we used x if we wanted to represent any number at all. So any integer, for example, is what we're really talking about here. So if we want to represent any integer, we call it x. What if we had to represent an even integer? Well, we start with an x that's any number, and then we call it 2x multiplied by 2, because any number multiplied by 2 will give you something that's even. That's the definition of what it means to be even. What if we have to represent an odd integer? Well, we take our 2x that we know is even, and we add 1 to it. Any even number plus 1 will turn it into an odd number. Okay, what if we have to represent consecutive numbers, like 7, 8, 9? Uh-oh, 6 is afraid. But how do we represent consecutive numbers? We take x, and then we add 1 to get the next number, x plus 2, and then we'd have an x plus 3, etc. If we needed consecutive even integers, 2x would be an even integer, 2x plus 2, which would be 2 more than that, would be the next even integer, 2x plus 4, 2x plus 6, etc. If you want consecutive odd integers, we start with 2x plus 1, which we said would be odd. Then we add 2 to it to jump over an even and get to the next odd. So we have 2x plus 3, then 2x plus 5, 2x plus 7, etc. Okay, they're helpful for us. Next one says, prove that the square of an even integer is always an even integer. And the proof is done for us here. Okay, so I don't know why this example 1 floated into the abyss, but it says let x be an any integer. So if x is any integer, 2x represents a general even integer. Okay, that's what we just established. So if we have to show that the square is always even, so we have to take 2x and square it. So 2x squared would be 4x squared, which another way to say that would be 2 outside of 2x squared. Okay, so since that's just 2 times a number, and 2x squared is an integer or any number at all, then 2 times it is an even integer. So the square also gave us an even. So therefore, the square of an even integer is always an even integer. These seem a bit weird, but they will get easier as we do more. Okay, two-column proof is just sort of a method that we use for proving that allows you to make a statement and justify it. We're going to see a lot more of this in our next unit when we do some geometry, but for now, we're just going to have a quick look. So we want to prove, it says, this is a property that we looked at in our last set of example questions. It says we want to prove that vertically opposite angles are congruent. So we want to prove, let's say, that alpha and gamma, that's what this is, a gamma, looks like a y, this is a delta, a beta, and an alpha. So we want to prove that alpha and gamma would have to be congruent angles since they're vertically opposite or across that x pattern. Okay, so here's what they did. They started by saying alpha plus delta is 180 degrees. And that makes sense because that's a straight line. Okay, they call that supplementary angles when they add up to 180. Then it says alpha equals 180 minus delta. So that's just subtracting delta from both sides of this equation. That's not hard. Then they're going to say gamma plus delta is 180 degrees. So gamma plus delta will be this, and that'll be 180 degrees. Yeah, that makes sense to me. And then by the same thing, they're going to say gamma minus 100, or gamma equals 180 minus delta just by subtraction again. Okay, that's good. So if that's the case, then alpha has to equal gamma because alpha is equal to this, gamma is equal to the same thing. If two things are equal to the same thing, they're also equal to each other. That's called the transitive property or transitivity. Okay, so we'll get more into two-column proofs in our last unit. So deductive reasoning allows us to draw conclusions that are irrefutable or always true. So the methods of proof are based on deductive reasoning, only when it's just proof. Okay? Number properties and tricks, we always generalize by using a variable and then use some algebra to get those other things. Two-column proofs are just a way of organizing a mathematical statement and their justification. Mostly used in geometry. We'll see them in the next unit.